Dear students, let's continue our practice on mathematics. And today's topic is maximum, minimum, supremum, infimum, and completeness of real numbers. So let's begin with the definition of upper and lower bounds, supremum and infimum of sets. So here, upper and lower bound. Firstly, a real number alpha is called an upper bound for C. C is here denotes a non-empty set of real numbers if x less than or equal alpha for all x from this set. The set S is said to be bounded above if it has an upper bound. So if for any x this is satisfied, x less than or equal alpha, any alpha real number, then we call it alpha upper bound of S, and the set S is said to be bounded above. Okay, and in analogous fashion, one defines a lower bound. So similarly, we can define a lower bound, and it calls a set that has a lower bound bounded below set. And now, let's give a definition for supremum and infimum. We denote supremum by sup and infimum by inf. A real number alpha is called the least upper bound. This is supremum. So supremum, it means least upper bound of S if, firstly, alpha is an upper bound for C, and secondly, there doesn't exist an upper bound for C that is strictly smaller than alpha. So it means this is least one. From upper bounds, least one we call supremum. So the supremum, if it exists, is unique and denoted by sup S. And now, infimum, it is the greatest lower bound. So, and we define this one analogically with infimum, with supremum, and we denote by inf S. So this is from lower bounds, the greatest one now. And here we have the epsilon definition of supremum and infimum. So we can define them by epsilon. Alpha, it is supremum if and only if, firstly, x less than alpha for all x, and the second, for every epsilon greater than 0, there exists x from S, from this set domain, such that x is greater than alpha minus epsilon. And the next one, for infimum, here we have the difference between them. Here we have x less than alpha plus epsilon. So it means we can find x such that which will be greater than alpha and minus epsilon. Epsilon, this is any small number here, small value. And now maximum and minimum. So the maximum, or just max, of a set S is its largest element if such an element exists. So the difference between max and the supremum, maximum and supremum. So if a set has a maximum, then the maximum is also a supremum for this set. but the converse is not true. So maximum point will be the supremum, but supremum is not maximum. And a finite set always has maximum, which is also its supremum, but an infinite set need not have a maximum. So if it is infinite set, we don't have maximum. Then the supremum of a set S needn't be an element of the set S itself, but the maximum of S must always be an element of S. And here are some examples that illustrate these differences. So in this case, let's take any set. So 1 minus 1 over n, and it's natural number. Then supremum of this set is 1, because here this is the goes to 0, 1 over n. If we consider, for example, if n 1, it will be 1. Then it will be 1 over 2. Then 1 over 3, etc. So it goes to 0 when n is increasing. So the greatest, the least upper bound here, we call it least upper bound supremum. So the least upper bound or supremum, in this case it is 1, but 1 is not a maximum, because maximum doesn't exist, because this is not finite set, this is infinite set. And in this case, in the second case, 1 over n here. So look here, why it's the supremum of the first example it's 1? Because this is 0. The least value, we need to find the least value of this one. It is 0. And 1 minus 0, this is 1. So this is the least upper bound. Yeah, we have the next, for example, we can take 2, but it's not least upper bound for this set. And the next example, 1 over n. Here the supremum is 1, because we consider this 1, it is the greatest value, it is 1 here. And the 1 is also maximum for this set. And the next example, so as it is the set of rational numbers such that x squared less than 2, then S doesn't have a maximum, but it has a supremum. The supremum of this set is square root of 2. But square root of 2 is not element of S. It's not included to the set of rational numbers, but it's element of R. So we can take as supremum square root of 2. I think it's clear why square root of 2 here, because it will be this is inequality, and the greatest value will be here square root of 2. And now let's consider any other examples. So the problem number 1, consider the set A minus 1 the power of n over n is natural number. So firstly, show that A is bounded from above. Find the supremum. Is the supremum a maximum of A? The next one, it is show that A is bounded from below. Find the infimum. Is this infimum a minimum of A? Solution. So what we have here, it is minus 1 the power of n over n, this set, yes? So what kind of elements we have here? If n is 1, it is minus 1. If n is 2, it is 1 over 2. If n is 3, this is minus 1 over 3. Then 1 over 4. So even terms are positive. Odd terms are negative. So here, what is the upper bound for this set? You can see all other terms will be less than 1 over 2. So the upper bound of A is 1 over 2. And now we need to show it. So let's take any m which is greater than 0 and let it be an upper bound of A. We'll show that 1 over 2 less than or equal m. So we need to show that we have a number which is greater than 1 over 2. So suppose the contrary, that is suppose that m is less than 1 over 2 now. M is less than 1 over 2. And since m is an upper bound of A, we have this minus 1, the power of n, our sequence, yeah, and it's less than or equal m. So we consider this contrary, and however m is upper bound, so satisfies this condition, this inequality for all n. In particular, letting n is 2, if we put instead of n 2, we get here 1 over 2 less than or equal m, which is from our assumption it is less than 1 over 2. Is it correct? No. So it's impossible. Thus 1 over 2 it's less than m. So supremum of our set, it is 1 over 2. So we showed that there are no other term which is there is no other term which is greater than 1 over 2. The 1 over 2 is the greatest one. So this is supremum, least upper bound. And since the supremum is an element of A, we conclude that 1 over 2 is also the maximum of A. So because the 1 over 2 belongs to our set, so it will be also maximum. And now the next step, find the show it's bounded from below and find infimum. Is this infimum a minimum of A? So here obviously we can see the minus 1. In our case, minus 1 it is least value in this sequence. So this is lower bound of A. And again, let's show m be a lower bound of A. We'll show that m is less than or equal minus 1. And again, suppose contrary. So we need to find a number which is less than minus 1. So that is suppose that m is greater than minus 1. And if we put 1, we have again minus 1 equal to this one, minus 1 over 1, which is greater than m by our from our assumption, and which is greater than minus 1. So, which is impossible again. It's impossible. Now, so if, however, we suppose contrary, it means the conclusion is m is less than or equal -1. So this is, we show it, it is bounded below. We need to show it bounded from below. And this establishes that in infimum a is -1. Since -1 is in a, it's a minimum of a. So it will be and infimum of a and minimum of a. Okay, the next problem. Consider the set A x, so such that 1, so in this interval, yeah, 1 and 2. Show that A is bounded from above, find the supremum. Is the supremum a maximum? And show that A is bounded from below, and find the infimum. Is this infimum a minimum of A? Okay, how to now so solution of this example again. So what we have here 1 and 2. So this is open interval. X belongs to 1 and 2, interval 1, 2, and here clearly the 2 is an upper bound of A. And again, let's show the by using the same method with previous example. So again, we'll show that 2 is less than or equal m. Again, we will suppose the contrary, and at the end we have that 2, it is the so 2 here we have it's a supremum, and so it is an upper bound of our set. And but in this case, this is not maximum because 2 not belongs to our set, because here we have open interval. If it is closed interval, for example, x is 1 and 2, from 1 and 2. So in this case, we can say the 2 is also element of the set, and this is maximum. But maximum should be from this set. And in our case, this is supremum. This is least upper bound to, it is supremum of A, but this is not maximum. Not maximum. Not maximum. So, and now, so this is lower bound. The 1 here is lower bound, and it will be infimum. 1 here is infimum also, but this is not minimum because it's not included to our open interval again. So if we consider this one, if we consider the closed interval, this one, in this case we can take as in minimum and maximum 1 and 2 respectively. But in our case, however, we have open interval 1 and 2, so we cannot take them as minimum and maximum. Okay, the next example. So consider set A, x greater than 0, and x squared, such that x squared greater than 4, and So what's the lower bound of A? Then let L be a lower bound of A such that L greater than 2. Let we have Y and show that Y lies between 2 and L. And the next case it show that Y from A and L, which is less than Y, show that this leads to a contradiction. Hence we must have L less than or equal to, which means that 2 is the infimum of A. So if the problem is clear, let's move to the solution of this problem. So since here we have x is greater than 2, here we have, yes, so it means that 2 is a lower bound of A. 2 is lower bound of A. And now the second case, in first case we need to find the lower bound. It is 2, just 2. And the next step, since L greater than 2, however this is lower bound, and we have L plus 2. If we add 2 to two sides of our inequality, we get L plus 2 is greater than 4. And it's implied that Y, which is L plus 2 over 2, will be greater than 2, because here that our Y was L plus 2 over 2, yes? And we showed that L is greater than 2 always. If you add both sides 2 plus 2, here we have L plus 2 greater than 4. So we can replace this L plus 2 with 4. It's greater than 4 over 2 or just 2. So we showed that Y is greater than 2. But in our case, however, L is greater than 2, so we can change this Y as L plus, it is L plus 2 over 2 in our case, and it will be less than L plus L. Now we will replace our 2 with L. So we have here now just 2, yes, 2L over 2, it is just L. So we consider that Y lies between 2 and L. This is false. Okay, now, so we did the second condition. And now the third condition is show that Y from A and L less than or equal Y leads a contradiction. So since Y is greater than 2, we have Y squared greater than 4, so that Y belongs to A. But L is a lower bound of A, so we must have where L is less than or equal Y, because this is lower bound. But this contradicts from the second case, B case, where we have Y, in this case, we have Y less than L. So this is contradicts with B, and it follows that 2 is greatest lower bound of A. So it is infimum. Okay, next problem, problem number 4. So for each following sets, S find supremum and infimum if they exist. So now let's consider the first one. So x squared less than 5, and if we solve it, it will be x minus 5, x plus 5, I mean square root of 5, of course, less than 0, or the answer is x belongs to the interval minus square root of 5 and the square root of 5. So square root of 5, it's upper bound of S, and but it's not maximum because it's not included to our set. And now this one, and similarly this is supremum of S, it is square root of 5, and infimum of S, it is minus square root of 5. And in the next one, it is x squared greater than 7. So let me write here x squared greater than 7. Let's solve this inequality, and we have x minus square root of 7, x plus square root of 7 greater than 0. And how can we solve? Here we have minus square root of 7. Here we have plus square root of 7. This is a matter of intervals. And plus minus plus, we have the whole plus. So x belongs to from minus infinity till square root of 7 is minus, and from square root of 7 plus infinity. So here we can see the supremum of this set is infinity because this is not finite set, and infimum of this set, it's also minus infinity. So we have the following answer. Now the third case, it is minus 1 over n. So let me write minus 1 over 1, minus 1 over 2, minus 1 over 3, etc. So in our case, the supremum of this set is 0 because it tends to 0, and it will be the least upper bound. And infimum of this one, it is minus 1 because this is greatest lower bound. Infimum of S, it is minus 1. So we have supremum and infimum of these sets. Okay, I think it's clear with supremum and infimum. And now, show that square root of 2 plus 1 over 2 is rational. And how can we show it? So let's suppose the contrary, and it means this is rational, not irrational, rational. So we can define this number as p over q, where p and q are non-zero integers. In this form, yes, so square root of 2 plus 1 over square root of 2 equal to p over q. And multiply through square root of 2, we obtain that it will be 2 plus 1 over square root of 2 equals to p over q. Hence, we have 3 equal to square root of 2 p over q. And now, hence we have square root of 2. It is 3q over p, which is rational. This is rational number, yes? This is rational. But this contradicts that fact that square root of 2 is irrational. So we have rational and irrational and rational numbers, and they are equal. It's not correct. So the assumption, when we suppose the contrary, we get the contradict. So it means this is irrational number. So this one is irrational number. This is irrational number. Okay, now let's talk about the completeness of real numbers. So we have completeness axiom. So any non-empty subset of R that is bounded above has a least upper bound. So one more time, any non-empty subset of R that is bounded above has least upper bound. In other words, the completeness axiom guarantees that for any non-empty set of real numbers S that is bounded above, a supremum exists. In contrast to maximum, which may or may not exist. And an analogous property holds for infimum also. Any non-empty subset of R that is bounded below has a greatest lower bound, so it is infimum. Yes, it is infimum. And now, Archimedean property, given any real number x, there exists n such that n is greater than x. This is we call Archimedean property. In other words, we say that the set of natural numbers is not bounded. So we can find every time the number which is greater than our previous one, any real number x. So this is Archimedean property. And the next one, it is completeness axiom implies Archimedean property. And here we have the proof idea. Assume n is bounded above, and by the completeness axiom, n must have a supremum. And say alpha is supremum of this set. And show that alpha minus 1 must also be an upper bound for n, and contradicting the definition of a supremum. So we cannot find here supremum. And the next one is completeness axiom implies monotone convergence theorem. And here also proof idea. So assume a sequence A and satisfy the assumptions of monotone convergence theorem. So it means it's bounded and monotone, say monotone increasing. If it is bounded and monotone, we say monotone increasing. Since the sequence is bounded by the completeness axiom, it must have a supremum. And let's take any alpha as supremum, and now use epsilon definition of a supremum to deduce that the sequence converges to alpha. So we can summarize that supremum of the set is least upper bound. This is supremum we call. And how to find supremum? We find from upper bounds for the set, and there doesn't exist an upper bound that is strictly smaller than supremum. And infimum, it is least greatest lower bound, and again we can find infimum from lower bounds. But remember, so here we showed that if a set has a maximum, this is largest element from this set, of course, it should belong to this set, and minimum, this is least element. So if a set has a maximum, then the maximum is also supremum for this set, but the converse, it's not true. So if we have supremum, not the maximum, we showed it in our examples. And a finite set always has a maximum, which is also its supremum, but an infinite set need not have a maximum. So I think it's clear with supremum, infimum, and maximum, minimum. So the next time we will continue our practices. If you have any questions, you can contact with us in discussion group. If you have any questions, any problems connected with our subject. So the next time we'll continue. Thank you for your attention. And in addition, I want to show some quizzes on Supremum and Infimum. So let's consider the set A, the following set, and here we need to find Supremum and Infimum of this set, and so how to find the Supremum and Infimum here? So the correct answer is D. So this is correct answer, and let me show how can we get this answer. So here, look here, this is sine, yes, and from trigonometry, if we put instead of n 1, in this case it will be 1 plus sine pi over 3, pi over 3. So sine pi over 3 equals to square root of 3 over 2. Square root of 3 over 2. And this is the greatest value of sine kt over 3, where k is sine k pi over 3. The greatest value here is square root of 3 over 2. So we cannot get here, for example, number which is greater than this number. K is the integer number. So it means we have 1 plus square root of 3 over 2. So it is 2 plus square root of 3 over 2. This is supremum of our set. This is supremum of A. And how get infimum as minus square root of 3 over 2? Because again, here the least value is minus square root of 3 over 2. This is least value because this is a p over 3. It's not p over 2, for example, or p over 4. So the p over 3, it takes from the greatest one is square root of 3 over 2. The least one is when it is negative. It is minus square root of 3 over 2. And in our case, it will be infimum. And because this is tends to 0, and it tends to minus square root of 3 over 2 as least value. So the correct answer here is this one. So infimum here is just minus square root of 3 over 2. This is infimum of A. Now let's consider the next example. Find again supremum, the set of A and infimum A. So here the correct answer is this one, C1. And let's solve this example now. So if we pick n as n1, we have 1 plus minus 1 power of 1 times 1 over 1. So it is 0. If n is 2, so we have 1 plus, let me write 1 because minus 1 the power of 2, and times 1 over 1. It is 1. Yes? Because 1 plus 1, 2, 2, it is 2, this is, yeah, this is 2, so we have here, here we have 2, of course, not 1, because we put 2 now, and this is 2. 1 times 2, it is 2, 2 plus 1, it is 3, and divide by 2, 3 over 2 we have. So it is 1.5. And now, if we put 3, for example, so it will be 1 plus minus 1 times 3 over 3. So this is less than this number. If you put 4, for example, we have 1 plus 1 times 4 over 4. So this is 5 over 4. And so it's also less than 3 over 2. So here we can see that 3 over 2, this is upper bound for this set, and this is least upper bound. So this is supremum of A. This is supremum of A. And now let's find the infimum of A. So in this case, again, if we can divide this fraction, so 1 over n plus minus 1 times the power of n over n. So they are cancelled, and we have 1 over n plus minus 1 the power of n. And now, so here the least value is equals to minus 1, because look here, this is 1 over n, and it is goes to 0. So this is greater than 0 always, and it goes to 0. And here we have just minus 1 or 1, because it depends on n. If it is even it is 1, if it is odd it is -1. So in this case the least value when it's 0 and when it's -1, so -1 it is infimum of our set A. And now the next one, so let A is the following set and find again supremum and infimum. So here the how to find the supremum now. So it -1, the power of n minus 1. So if we put 1, it will be, if we put 1, it is just 1, 2 plus 3. 2 plus 3, this is 5. So this is 5. And if you put 2, for example, it will be -1 times 2 plus 3 over 2. So it is minus 3.5. And if you put 3, for example, it will be 1 times 2 plus 1. So it is just 3. So we can see here, this is tends to 0, 3 over n in infinity. So 2 plus this, the greatest value of this one when n is 1. In this case, it takes a greatest value. So we took our greatest value. This is 5. So 5, it is supremum of A. This is least upper bound. And also we have here the infimum of our set. This is minus 3.5. This is infimum of A, minus 3.5, because this is greatest lower bound. So that's all. Thank you for your attention again.